All right, get ready to dive into the world of waves.
That's right, we're talking
You
waves.
guys sent in a ton of stuff for this deep dive,
Yeah, physics notes, course outlines.
even some experiment guides.
Yeah.
So it seems like you're ready to ride this wave of knowledge with us.
And we are absolutely stoked to be your guides.
You know what's funny, though? We see waves all the time,
Every day.
but I bet most people don't even think about the physics behind them.
Yeah.
So let's start with the most basic question.
Okay.
What is a wave?
So at its core, a wave is basically a disturbance.
Okay.
And it travels through space and time.
Okay.
It carries energy, but it doesn't actually carry matter.
Interesting.
Yeah. So think about like a pebble dropped in a pond.
Okay.
The water itself isn't actually moving outward.
Wow.
It's the energy from like the splash
Right.
that creates those ripples, and those ripples transfer energy across the surface.
I see. That's a really good visual.
Yeah,
So the water molecules aren't moving that far, but the energy is just rippling outward.
exactly.
It's kind of like when you do the wave in a stadium.
Yeah.
Everyone stays in their seat, but the wave of energy travels all around.
That's a great analogy, and it's that transfer of energy that makes waves so important.
Okay.
They carry information, light, and even help us communicate.
Wow.
Yeah.
I never thought of it that way.
Yeah.
That's already blowing my mind.
Right.
Okay, so we have this concept of energy transfer down,
Right.
but you guys also sent in some notes about different types of waves.
Yes.
We're talking transverse and longitudinal.
Mm-hmm.
What's the difference between the two?
So it really depends on how the wave is moving.
Okay.
In a transverse wave, the disturbance is perpendicular to the direction that the wave travels.
Okay.
So think of like a wave on a string. You flick your wrist up and down, but the wave travels horizontally.
So the energy is going horizontally,
Yeah.
but the actual movement is up and down.
You got it.
Okay, I think I'm picturing that.
Good.
So where does light fit into this?
Oh, light is a great example of a transverse wave.
Okay.
It's electromagnetic radiation, so its electric and magnetic fields are oscillating,
Yeah.
and they're perpendicular to the direction the light travels in.
Okay.
And another familiar example would be water waves.
Oh, yeah.
Think about how the water moves up and down as the wave travels towards the shore.
Right. Okay, so transverse waves, they move up and down.
Yes.
What about longitudinal waves?
So in a longitudinal wave, the disturbance is parallel to the direction the wave travels.
Okay.
So a good example of this is sound.
Okay.
When you speak, your vocal cords vibrate, right?
Right.
And that causes the air molecules to bunch up and spread out
Ah.
in the same direction the sound is traveling.
So it's like a chain reaction.
Yeah, and these compressions and rarefactions, they create a pressure wave.
Okay.
And that pressure wave is what our ears interpret as sound.
So sound is like a bunch of mini explosions.
Kind of, yeah. And that's also why sound can travel through different mediums,
Mm-hmm.
like solids, liquids, as long as there are particles to vibrate and carry that energy.
Gotcha. Okay, that makes a lot more sense.
Good.
So we've got these two basic types of waves.
Uh-huh.
They're all around us, but how do we actually measure them?
Right.
What are the characteristics we need to know?
Yeah, so there are a few key terms that we need to define here.
Okay.
Wavelength, amplitude, frequency, period, and wave speed.
Those are a lot of terms.
I know, but they're all interconnected, and they help us understand how a wave behaves.
All right, well, let's break it down.
Okay.
Let's start with wavelength.
Okay, so wavelength is simply the distance between two consecutive corresponding points on a wave.
Corresponding point.
Yeah, so for transverse waves, think about the distance between two crests.
Okay, the peaks of the waves.
Yes, exactly. Or for longitudinal waves, it would be the distance between two compressions.
So if you imagine a water wave,
Uh-huh.
wavelength would be the distance between two wave tops.
You got it. And we measure wavelength in units of distance.
Like meters.
Meters, centimeters. Yeah.
Okay, I'm with you.
Good.
Now, what about amplitude?
So amplitude is a measure of the wave's intensity.
Intensity.
Yeah, or energy.
Right.
Think about it like this. A loud shout has a higher amplitude sound wave than a whisper.
That makes sense.
For a transverse wave, we measure amplitude as the distance from the resting position to the crest or the trough.
So a taller wave has a larger amplitude and carries more energy.
Precisely.
Okay, that makes sense. So what about frequency?
Okay.
I know that it has something to do with how often a wave repeats itself,
You're on the right track. So frequency is the number of waves that pass a given point
Mm-hmm.
in a certain amount of time, usually 1 second.
Okay.
It's measured in hertz,
Words.
which means cycles per second.
Okay, so if I see 10 waves pass a point in 1 second,
Yes,
that means the wave has a frequency of 10 hertz?
exactly. And higher frequency means more waves are passing by, so that also means more energy is being transferred.
Wow. Okay, I'm starting to see how these pieces fit together.
Good.
Now, what about the period of a wave?
Okay.
Is that just how long each wave lasts?
You're close. So the period is the time it takes for one complete wave cycle to pass a given point.
So it's like the duration of a single wave?
Yeah, it's basically the inverse of frequency.
Inverse.
Yeah, so a high frequency wave has a very short period,
Okay.
and a low frequency wave has a long period.
So if a wave has a frequency of 10 hertz, meaning 10 waves pass a point in 1 second,
Yeah,
the period of each wave is 1/10 of a second.
exactly. You're getting it.
All right, last one. I think this is where things get really interesting.
Okay.
Wave speed. How fast do these waves actually travel?
So wave speed is how fast a wave moves through a medium.
Okay.
And here's the key. It depends on the frequency and the wavelength of the wave.
Oh, so they're connected.
Yes, and there's actually a simple equation that ties it all together.
Really?
Yeah, wave speed equals frequency times wavelength.
Oh, wow. So if I know the frequency and the wavelength,
Yes.
I can calculate how fast it's traveling.
You got it.
That's amazing.
Okay.
Okay, so are we ready to, put this knowledge to the test?
I think so, yeah.
All right, let's see what we can do with this wave speed equation.
Okay.
Looking at my notes, and I see an example here.
All right.
It says a wave has a frequency of 5 hertz
Okay.
and a wavelength of 2 meters.
All right, so we can use our equation, wave speed equals frequency times wavelength,
Okay?
to calculate the wave speed.
So 5 hertz times 2 meters,
Mm-hmm.
that gives us a wave speed of 10 meters per second. Is that right?
You nailed it. 10 meters per second.
Wow.
Yeah, it's kind of like figuring out how fast a car is going.
Okay.
If you know how many times the wheels are rotating every second and the circumference of the tires.
That's a good analogy. Okay, I'm feeling more confident now.
Good.
Let's try another one.
Okay.
All right, this time it says a sound wave travels through air at a speed of 340 meters per second
Okay.
and has a frequency of 256 hertz.
Right.
What is the wavelength of the sound wave?
Okay, so this time we have to rearrange our equation a little bit
Okay,
to solve for wavelength.
gotcha.
So wavelength equals wave speed divided by frequency.
Okay, so we've got 340 meters per second divided by 256 hertz.
Uh-huh.
That gives us, let me see, about 1.33 meters.
Exactly. So that means that the distance between each compression
Okay,
in that sound wave is about 1.33 meters.
this is pretty cool.
Yeah.
I'm starting to see how we can use these equations to figure out all this stuff.
Yeah, it is kind of like a puzzle.
Yeah,
And each piece of information gives us a better understanding of how waves behave.
right.
Now, remember how we talked about waves carrying energy?
Yes.
Well, that energy can actually be affected by a wave's amplitude.
Right, amplitude, the measure of a wave's intensity.
Yeah.
So does that mean that a larger amplitude means the waves is carrying more energy?
You got it.
Okay.
Think about it like a tsunami.
Oh, wow.
Massive waves, huge amplitude,
Yeah,
carries way more energy than just a little ripple in a pond.
that's a very dramatic example.
It is, but it makes sense.
It does. It does. So how does amplitude actually relate to the energy carried by a wave?
Right.
Is there a way to calculate that?
There is.
Okay.
The energy carried by a wave is proportional to the square of its amplitude.
So if you double the amplitude.
You quadruple the energy.
Wow.
It's a pretty powerful relationship.
Yeah, I'm starting to see how even small changes in amplitude
Yeah,
can make a really big difference in the amount of energy a wave carries.
exactly. And this principle is at play in so many different applications,
Like what?
like sound amplification systems and even like the design of earthquake-resistant buildings.
Wow. Never thought about that.
Yeah, but waves don't always just travel in a straight line forever.
Right.
They can interact with their surroundings in all kinds of interesting ways.
Okay.
Have you ever wondered how waves bend around corners?
Yeah, like I can hear someone talking around a corner, but I can't even see them.
Right.
I've always wondered about that.
That's a great example of diffraction.
Diffraction.
Yes, it's the bending or spreading out of waves as they pass through an opening or around an obstacle.
So it's like the wave is sneaking around the corner.
Kind of, yeah. And the amount of bending actually depends on the wavelength of the wave and the size of that opening.
So longer wavelengths diffract more.
Yeah, that's exactly why AM radio waves,
Okay.
which have longer wavelengths than FM radio waves,
Right.
can travel farther and be received in areas with more obstacles.
Cool, like hills and mountains.
Exactly.
Oh, that makes sense.
Yeah, it's like those AM radio waves, they're better at navigating
Uh-huh.
because they're longer and they can bend more easily.
So diffraction is what lets those waves reach my radio even when I'm driving through like a valley.
Exactly. Diffraction is super important in how we experience sound and other types of waves every day.
This is mind-blowing.
I know, it's pretty cool.
Like this whole hidden world that we
Yeah.
don't even notice.
Right.
But there's one type of wave we haven't talked about too much yet. Light
Uh-huh.
waves. I know those waves can do some pretty amazing things too, right?
Absolutely. Light waves are really remarkable.
Yeah.
And they're a perfect example of transverse waves.
Okay.
And their behavior can be explained by a lot of the same principles we've been discussing.
So do light waves also diffract?
Yes.
What about their speed? Do they travel at different speeds depending on their wavelength and frequency?
Those are great questions, and that leads us into some even more fascinating aspects of wave behavior.
Okay.
Why don't we dive into the world of light and explore those questions next?
All right, let's unravel these mysteries of light waves.
Okay.
We talked about how they're transverse waves,
Yes.
but how do they diffract? What determines their speed?
Well, light waves definitely diffract like sound waves.
Okay.
Think about when light passes through a narrow slit.
Uh-huh.
It spreads out and creates a pattern of bright and dark fringes.
Yeah. I've seen that in physics demonstrations.
Right.
It's like they interfere with each other
They do.
and make those patterns. What about their speed, though?
Okay.
Does that wave speed equation still work for light?
It does, but there's a twist.
A twist.
Yeah, light waves have a constant speed in a vacuum,
Okay.
which we call the speed of light.
Oh, right.
It's incredibly fast.
Yeah. How fast is it?
About 300 million meters per second.
Wow, that's so fast.
It is.
So no matter the frequency or wavelength, it's always traveling at that same speed.
In a vacuum, yes.
That seems kind of counterintuitive.
It is pretty mind-boggling, but it's one of the fundamental principles of physics.
Wow.
But here's where it gets interesting.
Okay.
When light travels through different mediums,
Uh-huh.
like water or glass,
Yeah.
its speed changes.
So that's why light bends when it goes from air into water.
Mhm.
Refraction, right?
You got it. Refraction is all about waves changing direction
Okay.
when they go from one medium to another because their speed changes.
Okay.
When light enters a denser medium,
Yeah.
it slows down and bends towards the normal.
Normal.
Yeah, that imaginary line perpendicular to the surface.
Right. Okay.
Yeah, so that's why things underwater look distorted.
Oh, yeah.
Or they look like they're in a different spot.
Yeah.
It's because the light waves are bending as they travel from the water to the air.
Oh, that's so cool.
And it gets to our eyes.
So that's how we see it.
Yeah, exactly. And this principle of refraction
Uh-huh.
is how we make lenses for eyeglasses,
Oh.
microscopes, telescopes.
Okay.
By shaping the lenses, we can control how the light bends,
I see.
focusing it to create magnified images or clearer images.
That's incredible.
It is.
So we're harnessing the power of waves
We are.
to enhance our vision.
Yeah,
That's amazing.
it is. And it's not just vision.
What else?
Refraction is also really important in fiber optic cables.
Uh-huh.
You know, those thin glass fibers
Yeah.
that transmit data super fast?
Yeah.
Light signals are trapped in the fibers.
Okay.
They bounce back and forth
Yeah.
because of total internal reflection, which is another wave phenomenon.
Wow. So all those videos and messages
Yeah.
are going around the world because of how light waves behave.
Absolutely. It's pretty amazing to think about
It is.
how these invisible forces are shaping our world.
This deep dive has been incredible.
What has?
We've explored so much about waves,
Yeah.
learned how to describe them, see how they work.
Mm-hmm.
I mean, it's crazy to think that from the sound of our voices to the light from stars,
Yeah.
it's all about waves, carrying energy and information.
It really is, and we've only just scratched the surface.
I know, I can't wait to learn more, but thanks for joining us for this deep dive into waves.